Hello, everybody. Good afternoon. My name is Yvette Subramanian. I work here at Citrus, and I'd like to welcome you to today's Research Exchange. We are honored to have Professor Marcello Kallmann from UC Merced, and he is going to talk to us today about his work with virtual characters, avatars, and motion interfaces for improving physical therapy. I'd like to welcome our web viewers, everybody. As you know, these are viewed. The other campuses get together and view them on Davis, Merced, and Santa Cruz, and they can use the Twitter hashtag CitrusRE to ask questions, and we will ask them of Professor Kallmann, or I will. I'll get them and ask you. So I'd like to introduce Professor Kallmann. He's a founding faculty and associate professor of computer science at UC Merced. Before he went to Merced, he was at a computer science department in University of Southern California, and a scientist at the USC Institute for Creative Technologies. He got his PhD in 2001 from the Swiss Federal Institute of Technology, and his research includes computer animation, virtual reality, and humanoid robots. So please join me in welcoming Professor Kallmann.
So thank you for inviting me to come here. It's a pleasure to come and visit Citrus here. And what I'll be talking about is mainly about the goal of achieving an autonomous character that can play the role of an autonomous demonstrator. So we would like these characters to be able to perform motions that look human-like and that follow high-level specifications. And by high-level specifications, I mean two main things. One is the usual kind of a task specification. I would like to point to specific targets or perform specific actions. But I would like as well to have these motions to look like given examples so that we have a way to control in which way you would like to learn from given demonstrations that these characters would be performing. And that comes with the idea of learning by demonstration, where we're going to see how we can demonstrate example motions for given actions and reuse them to have the autonomous character to perform demonstrations, but then autonomously in arbitrary environments by adapting these example motions. And this is what I'll be referring to as the problem of human-like motion planning. And really the goal here is not to be extremely realistic or emotional in terms of the kinds of motions, but to be able to adapt these motions to the environment and different tasks and produce motions that are similar to the given examples. In this way, we have control on how these demonstrations will be performed. And then, of course, if we use this character in interactive applications, then the users can be tracked, and we can think of many applications with interactivity between the user and the virtual character. And of course, there are several applications that we are looking at in traditionally training, ergonomics, education, therapy. You'll be seeing along the slides different configurations using our Powerwall, the 6-tile immersive visualization system, other examples based just on a small desktop and Kinect. So many configurations are possible. Many different kinds of motion sensors are possible. And you'll see a variation of these things along the slides. And I'll show some first examples of applying these ideas to physical therapy application. This is in collaboration with Dr. Jay Hand from the UC Davis Medical Center. And we actually had a meeting yesterday, and our tech transfer office asked us to not present, so that I was asked to not present our latest results on that area, so I'll be just doing an overview of what we are doing there. And then in this talk, I'll mainly be talking about motion planning algorithms and how we are adapting them in order to be able to perform demonstrations that look like example motions, and we are going to apply these algorithms to motion capture databases. And as well to achieve whole body coordination between these tasks. And then I'll make an overview of the applications to physical therapy. So here is one example. If we just apply motion planning algorithms for virtual characters to perform motions or demonstrations, actions like these ones, this is the kind of quality and results that you get. So this is really using standard algorithms, sampling-based algorithms, and there is a good summary in this 2006 book of Stephen Laval from these algorithms. And this is a work from 2003 where we applied several concepts from computer animation in order to be able to use these motion planning algorithms. And we can get interesting results, but still it misses some sort of human likeness on these motions, and it's difficult to control how the motions should be performed. So some of these images are actually used as examples in this book. And these algorithms work by sampling several postures of these characters. It's a high-dimensional space. And then trying to connect these postures in order to create a graph of possibilities. And then we can do graph search in order to find a solution around the obstacles, around the constraints, in order to reach goals. And in this particular example, what was important is really to have a good modeling of the skeleton in order to achieve reasonable motions. And we start with per-articulation, parametrization, and range limits. And as well, when we're sampling postures, we need these samples to be meaningful. And examples of some of rules that we have to include is to have couplings. And for instance, for distant reachings, we don't want to have the character reaching forward and bending leaning the spine backwards, right? So it doesn't look coordinated. So we can think of several rules in the same way if we're reaching high targets, we don't want to have knee flexion. So we cannot just blindly sample all these degrees of freedom. We need to follow some rules to have some human-like postures that are meaningful. And that is what we did. And then once we are able to sample several of these motions, we then can evaluate transitions between two nearby samples. And every transition will become a small piece of motion that will test for enforcing balance constraints, limits, to be collision-free. And with that, we can connect all these pair of transitions that are valid and build graphs. And this is an example of these graphs. And this is called in the literature a pre-computed roadmap. And here in this graph, every node represents where the hand can reach, but each node is associated with a full body configuration. And actually, we simplify the full body configuration by a 22 degrees of freedom control layer. And for instance, you saw in the example that knee flexion is controlled only with one translational, vertical translation degree of freedom. And then with inverse kinematics, we figure out what are the joint angles of the legs to achieve that amount of knee flexion. So doing that control layer to simplify the problem, and we can kind of have a representation of the reachable volume for this character, and that we can search for solving problems, right? Now, there are difficulties in this kind of methods, of course, and to the motion planning problem in general. So this configuration space are very easily get really high dimensional. And it's just not possible to do a complete discrete search into this space. We can sometimes apply collision avoidance methods without trying to run complete or more extensive planning and search methods. But however, as soon as you get a little bit more cluttered environments, then the collision avoidance method will as well not work well. These sampling-based methods do work well. They're very popular, and they're mainly from robotics, right? They're very used. But in our case, they're not really real-time for our applications. So we can get results in 1 or 2 seconds, right? But it's difficult to guarantee being faster than that. We often need post-processing of the motions because the first solution is a connection of random samples, right? And then we need to smooth and optimize the obtained solutions. And it is difficult to address balance constraints and locomotion. So what you saw before, the feet of the character was planted on the floor, right? So that is much easier because we have less constraints when we are connecting samples. Now, how can we address these constraints? And this is the work we've been doing. We've been relying on motion capture both to reduce the dimensionality of the search space and to increase the quality of the produced motions, right? So we are using, we could use different technologies that are now available, but we are using these Vicon camera systems where you can track very reliably markers that we can place on a full body and reconstruct very precisely a given motion. And here is an example of how much the quality improves when we use motion capture. So in this problem, we are using a walking motion capture animation, and we're not modifying that walking, so the walking looks very realistic. But then if I just place an umbrella on the hand of the character, the umbrella will collide with this pose. That's where we need some planning to get around the obstacles. And then we are doing planning only for the 7 angles, the 7 degrees of freedom of the arm in order to find a solution for manipulating the umbrella around the posts. Now, for that to work in synchronization with the motion capture file, these are examples of solutions that you can get. We need to synchronize with the timing of the animation. And the search then happens at the configuration time space of the arm. And then we can place it on top of the character and we can address dynamic targets, dynamic objects, because everything is time parameterized. So we can see that the quality of the solutions greatly improve, although we're not doing something to try to ensure coordination between the upper body and the locomotion part or the lower body animation. So we actually need to have as well control over the locomotion, and we need to plan both the locomotion and the upper body actions. And that is very important to place the character, or in this case, this humanoid robot, in the right location in front of the place that the task is to be performed. So if the positioning is right, the task of performing the action shouldn't be difficult to plan, to find a solution for. So we have to address both of the problems together. So this is an example without motion capture, just using what's called in the literature a multimodal motion planning approach, where basically we're dividing the problem into small problems, and we are planning the motions of the legs individually. We are also planning small shifts on the body position so that we can transition the support foot from one to the other by moving the center of mass from left to right. And we are planning the arm independently as well. And then as we plan these different modes or skills independently, we also search for the best combination and sequencing between these primitives until we can get the solution. So this was a work that we applied for this Fujitsu small humanoid, but the problem is exactly the same for our virtual characters. We have to address coordinated motions together, the positioning part, approaching the target, and then the action performance. Now these algorithms, of course, you can just use them and apply them to virtual characters, right? But the motions just don't look good, right? So there's a lot of stepping around because this is the easier zone for the algorithms to find solutions. And we would like to improve all that, right? So what can we do to improve this? And then, again, so we need to improve the motion quality, and we're going, again, to reuse motion capture. And we would like to improve the coordination between the motions, not having many steppings, for instance, or having meaningful orientations and gaze behavior and all that. So how can we improve the locomotion part of it? So this is a traditional topic in computer animation. There are lots of research groups working on locomotion models. And in the past few years, in particular, there has been a lot of research on these areas. And we are following one popular group of approaches based on what's called motion graphs, which is, again, based on a collection of motion capture clips that we put together by evaluating transitions between these small clips. And we have working on that, and we have found out that with a specific way of segmenting these motion capture clips at a particular location, and that location is actually when one foot traverses the vertical plane of the body. That is where you have a single support mode that makes a perfect place for blending into other similar frames and creating transitions in that way without introducing artifacts like fit sliding when we blend and concatenate these motion examples. So by doing that, we also are able to compute graphs much faster, and we can do some optimization of solutions with some inverse kinematics kind of optimization to adjust the concatenated solution towards precise targets, which is something important for us. And we can also achieve interactive solutions at interactive rates by using some precomputation. So let me tell you a bit about the precomputation. So each red segment that we see here is one motion clip of one cycle of a walking motion. And then by concatenating all possible walking clips that concatenate well to each other in that given database that we are using, that's after 5 concatenations, that 5 or 6 that we see here, this is the kind of space that we can reach from the given initial position at the top, and by all the possible concatenation, this is the kind of space that we can reach. So we can pre-compute these concatenations and these, what we call these motion maps. And then when we have a problem to solve, like for instance, to reach a given goal, or to, in this case, to follow a path. So here we have a path that was planned in 2D very fast using geometric algorithms. And then the problem now is how to use our locomotion database to synthesize a nice locomotion sequence following these paths. And then we're just overlaying those pre-computed maps on top of each other and picking the best branches that will follow the path. And then we can get nice solutions that are very close to the original quality of the recorded database. And we can have not only good control of to follow paths or to arrival locations, but we also have choices of choosing small differences, a branch a little bit to the right or to the left, and we can use these variations to make better choices later on when we would like to connect to upper body actions. So this is an example of interactive application showing that with the pre-computation, these planning problems can then become very, very efficient. Of course, not really real time, but maybe half of a second you can find reasonable solutions in reasonably cluttered environment. Okay, now, so we would like to do a similar strategy for the upper body, right? Now, the upper body, the problem is upper body actions. The problem is a little bit different. I'm not really interested in concatenating small pieces, but I have to have a flexibility, a variation of my actions around the workspace in front of the character. So the approach we're taking here is to, again, start with the database of motions, but these will be example motions for one particular action, and these example motions are modeling variations, different strategies that are of interest to the given application of performing the same action. So we have then to align these example motions. You can think of these stacked colored bars here as different example motions that are aligned, and they have meaningful, they are representing the same kind of action just with variations, so that if we blend them, if we interpolate these examples, we'll still have a meaningful variation of an action, right? And how we blend these examples? Well, we just decide a given set of weights. There is this W weight vector. And then we do this average interpolation of these motions. We have a blended new motion that is the result of combining with different weights the example motions together. Now, but the problem that we want to solve is actually the inverse of doing the motion blending, is what we call the inverse blending problem, which is given constraints that we would like to address, for example, precise targets to point to or to reach with the hand, I would like to find the blended weight such that the blended motions will result in a motion that will satisfy my constraint or my target, right? And we can solve this with a simple optimization problem that will do a few iterations to optimize the weights until we get as close as possible to the target. And if we build these clusters of example motions well covering the search space, then this optimization can work very well and just a few iterations to find solutions. And here are examples of kinds of targets that we can address, like pointing a directional constraint so that we do pointing in a particular direction to identify objects. Vertical constraints, I would like to pour water on top of this container, right? Then we have a collection of examples of pouring actions, and then we just blend them. And this is the interesting thing, which is if the clusters are well built, when we do this motion blending, the solution keeps the original quality of the pouring water. So we're not doing any physics computation, nothing expensive here. And on the last example, going to precise targets for pressing buttons and so on. Here are some examples of some of these tasks. So now pointing to precise locations. And then we have a database of several motions around the workspace. And we select the nearby examples, do optimization on the blending weights, and find the combination that will go to the desired location. Here is just a vertical constraint to deliver the water at the right location. Now, what is interesting about this approach is that we don't really need to have our blending weights to be fixed over time along the duration of the motion. So we can have these weights to vary, and that opens the possibility to do more search in order to adapt to the new environment. So for example, here, if we are blending 3 example motions, we could decide on the first part of the motion to have most of the contribution from this blending coming from motion 1. But then by the middle of the motion, I will have more contribution from the second motion. By the end, I'll have more contribution from the third motion. And what we're doing here is varying along the way on which parts, which contributions from which example motion we would like to use more or less, right? And with this idea, we can then apply again a sampling-based search and try to explore all possible combinations between switching through our strategies encoded in this cluster of example motions. And this is what we've done here. We have developed a method where we started the solution that will go to the goal just using this inverse blending method. And then we detect if that solution is valid, respects all constraints, does not collide with objects. If there are collisions like that middle part in red, then we remove that infeasible part And then we start sampling and connecting feasible nodes, feasible new poses that are checked in workspace, but that were sampled on the wait time space, right? And then we connect to the closest node on the current available correct solution, feasible solution, and we keep expanding these nodes until we find a new connection to solve the task. So with that, we have, in the end, the solution is a sequence of waits to use along the solution motion. Then we can reconstruct the final motion by smoothly interpolating this sequence of weights. And so here are examples of what we can do. And then we can choose. So how many examples do we want to choose so that the sampling, the number of, the dimensionality of the search space is reduced to the number of example motions being considered. And that the example motions can be modeling examples for the full body animation, right? So that's a good way to reduce the dimensionality of the problem. So here in this top sequence, what we see is a solution. The initial solution was colliding with that green object, but then the strategy that this solution found was to point to the target going over the obstacle, and that was found because there was one example motion that was doing that, right? So if you decide that maybe I would like to have pointings, lateral pointings like that, then you can include that in the database, and the sampling will evaluate using that solution, right? On the bottom sequence, what you see here is the left arm goes backward to assist with balance, but I mean, the planner is not computing that. That is just something that was captured as part of the example motions. That was a style of the performer that did this balance strategy of putting the arm backward. So that these things come for free, and one advantage of that is that we will not see surprising solutions that you didn't think that would make part of a solution, because we're just reusing what is already there. Now, we would like as well to coordinate the upper body actions with the locomotion. So here is how in the end, our planning problem will be solved. So we start with the locomotion planning that we saw before, where we are sampling locomotion pieces and concatenating them. And we are opening this search tree of possibilities, right? And we keep expanding that until we are close enough to the goal of the action. So when we detect that we're close enough, like to an arm length distance to the target, that's where then we're going to search, use the action cluster that I can use for search in the blending space of that action cluster. And I'll try to solve the action problem from that positioning of the body character at the configuration QA there. But I will not want to explore too much in order to solve the action from that position. So after a few expansions, I will just stop that search, because I don't want to find a solution that is awkward and has a lot of variations between my examples. So instead, I would like to halt that after a few iterations. If I didn't find a solution from that position, then I'll let the locomotion to explore other ways of approaching the target. And eventually, we should find one way, if the scenario is well modeled, where a very simple, less expansions on the upper body action should be enough to perform the task. And then the first connection that we find, we can just use that. That's one solution. Or we could as well find more solutions and then try to choose one that has some properties that are more interesting for the application, minimizing distance travel or something else. So here is a few examples of combining all this together. So starting with the locomotion planner, then it goes around the obstacles until it is close enough to perform the upper body action. In this example, there are no obstacles for the upper body action. Then there is no search, just the solution from the blending the examples is used for that pointing motion. And this is the example where there was a collision, and then this is the final solution by using the pointing strategy of going upwards to that target. Here's another example that found a pointing, putting water motion that could go in between those two vertical objects. Of course, for that to work well, it's important to, again, to synchronize with the locomotion, so that we need to be at the right location so that the action is performed without much deformation and reaches the goal. So it's very important to include the locomotion into that, because both have to work in a synchronized way. And we are actually exploring the different trade-offs of how much effort to apply on the locomotion side and on the action planning side. Now, Another point that it is important for our target training applications is that in most of the time, we are delivering some training information, what to do with some objects or how to perform some tasks, to a given person, to given observers. And we have to coordinate visibility of the observers and orientation, eye contact, and all these things, right? So we need a higher level coordination model to ensure that these these demonstrations are well delivered. And what we did to get there, we performed several evaluations with human subjects where we asked people to approach a table, walk towards a table, approach a table, and point to different objects placed at that table, and do some explanation about the objects they see there in that table. So you see these in the left. It's not actually a real table. We are using this grid, and this is so that we don't have visual occlusion with the motion capture cameras. And then we are and there are small objects placed on that horizontal grid where the user can see and then tell something about these objects. And we are tracking then the full body motion of the person there. And then we're asking several subjects to do these demonstrations to these many objects, plus in respect to observers, and these are the VP little squares that we see there, to observers placed on different locations on the other side of the table. So then we have someone else standing on different positions, and we ask that information to be delivered to that person at that location. And then with that, we have a good selection of variations on the typical scenario of deciding where to go, pointing to an object and delivering some information to someone at a given location. We then annotated all these captured information and analyzed all the data, and we built a model to try to model the main parameters out of that. Here are the main parameters that we extracted from this model. And these are basically encoding the relative positions of the main elements there, the demonstrator position, the viewer position, the target position. And within relative angles between them, the angle between the viewer location with respect to the demonstration, to the demonstrator, the angle between the demonstrator location with respect to the target, between the demonstrator orientation with respect to the viewer, and as well the range of head rotation during gaze between focusing at the target to go, as well to where the table is that we want to decide where to put your foot for the last step before performing the action, and then looking at the observer as well. And we have all these event timings, these ranges of angles that were observed, so we have an acceptable range for these angles. And we have as well discovered other constraints that are always there. For instance, a very important one is to ensure mutual visibility. So the demonstrator will always have visibility to the target, to the observer, and the observer should also have visibility to the target. And then we built a model on what are acceptable ranges for all these parameters. And we built a planner that would find solutions within these bounds, this model. So here is one example. And this is really ongoing work. And what you see here is we have the yellow character that is supposed to make a demonstration at that action gesture target location on the top for an observer located at the bottom. And then we are looking around the target location for feasible body placements that have enough space for the character to be, that has locations that have a connection to the initial location of the character by checking geometrically if is there a path with enough clearance to get there, and a location where we allow to preserve all these mutual visibilities. And we see in this example that we had to have the character to make that turn to orient itself such that the observer has visibility to the target. Otherwise, the body of the demonstrator would block visibility between the observer and the target. And then we look for these possible placements. Once we have the placement, then we can run our search methods that we saw before and synthesize a locomotion sequence that will go to that location and then perform the upper body action. So here is another example. So that's a more simpler solution where the demonstrator could be right in front of the observer and the target at the same time without having any occlusion. And there was a path to go there. In this example here, though, we had to go through a path along the right side, and stay in a sideways position because if you were demonstrating from the other side of the table, that would make more sense to be in front of the observer. We would not have visibility because of this middle obstacle at the center of this room, right? And that was a location, by searching around all possible locations, that was a location that ensured all these multiple visibilities. And so again, this is a higher level planner that will specify these target locations that will conform to our high level coordination model for this demonstration of tasks. And then we can synthesize the animations on top of that using all the methods that I presented before. And that is very efficient because it only relies on fast geometric computations in the environment. And there are only few positions evaluated around, right? It's not a continuous space. We just sample around some possible body placements around the target and we evaluate the ones that best satisfy our coordination model. And then for each one that is feasible, then we try to get a solution towards that location. Okay, so let me move on now. So I hope that made an overview of what are the methods that we can develop to address these whole body motions for demonstrations with acceptable quality and controllable quality, right, from examples, and enough coordination to deliver information, tasks for observers in a meaningful way. Now, I'd like now to do an overview of some of the applications that we're applying these methods. We're starting to apply some of these methods. And the first application is a more generic training application to deliver information about workspaces or objects. And what you see here in this example is on the left, we have this stereo system. And we would like just to tell if you press this button, that happens. Don't do this fast, do this slowly, and pay attention to here. And then in the end, we are asking the person who is modeling this environment, okay, organize your motions into clusters of actions that we later on can interpolate together. And by demonstration, record example motions for each of these actions that you would like to have in this environment. And then save them. And then later on, the virtual character, and then that's the testing or training phase on the right, the virtual character can reuse this set of motions and again deliver the information to generic locations. The user can then click any location. The virtual character will then go and demonstrate the actions there. And the actions are generic. We are recording from motion capture what is the action that you would like to do. So here's an example of pointing, right? So we're just pointing to given locations. So maybe the pointing that you are recording is not any kind of special pointing. Then just moving the hand there would work well. But sometimes we would like to do some pointing with giving some expression. And the motion capture will just record your examples, right? And then interpolate the example. So it's up to the modeler, the designer here, to decide how to create this cluster. But once they are done, then we can reuse them for generic constraints. So here's an example showing, we are also using a data glove, so it is, of course, also possible to capture finger motions that sometimes, most of the times, are important as well, right? And here's just a recording and playing back, and we have interfaces for you to save and load, trim the motions, and model them. And here's another example of putting water, and maybe it makes sense to hold a cup of a mug there, so that helps you to feel the weight and do the action more properly. And then later on, after these clusters are modeled, then we can ask, okay, do this action to this location, to that location, right? And at this point, we are ready to have higher level scenarios specified in order to do some training to deliver some information. And then there are several possibilities on how to develop a user interface to make this system usable. So we have here some examples using the motion sensors to visualize the motions that you have just recorded. At the bottom, for each cluster of example motions that you create, we would like to visualize how well that set of example motions is covering my workspace of interest. And on the left, you can have a global view. On the right, we can look to specific targets. If you would like to precisely place the finger, those buttons at the telephone there, then maybe we need more examples around the telephone, right? So that we can interpolate well around that region of interest. And by putting together all these elements, then we can get to an application where at least you don't need to have skills in modeling applications like 3ds Max and Maya. You can use your own demonstrations to create new scenarios. And this whole concept applies directly to the problem of performing motion exercise. And here is where this is useful for physical therapy. So we are exploring 3 directions. So once we built all these ideas into a system, there are many things that are obviously easy to do. And the first thing is we can customize exercise because we can have motion capture to allow therapists to create any kind of exercises specific for patients, and just by demonstration, right? And then we can record them, and then again, in the same way, we can reuse them and have the virtual character, now the virtual therapist, to deliver these exercises to people and have the people to follow these exercises. And we see already some of these things going in kind of a video game exercising application for game consoles, right? So some of these things could be running at home based on Kinect. And if everything is being tracked and modeled, we can also do remote collaboration, right? We can use these virtual characters as avatars that are actually showing the motions of the real patients or real therapists at distant locations, representing them on the virtual environment. And then both the patient and the therapist can, one can follow the motion of the other, and they can have like a remote consultation, remote interactions inside the same virtual environment by streaming the motions to each other. Now, since we rely on avatars, right, and we need to track the users and we need to extract joint angles, and depending on the tracking technology, this can be easier or more difficult, but at least when we get to the joint angle level, then it's much less data to transmit over the internet, and we're not sending geometry information of all the, or video information of the appearance of people. So here is an example using our Powerwall setup. And this is, again, using a few markers of the Vicon tracking system. We're not tracking the full body, just a few markers on the hands, the head, and at the back here. So just for upper body motion tracking. And this is an example of an interface where you have a few controls there to say, okay, start recording. And we also, in this case, we also have a Wiimote controller on the right hand that have buttons to say stop recording, replay, and so on. And here we are just recording one exercise, and these are simple arm motions. And you can then visualize them back again. That is an example of this slider moving back and forward. And once we're happy with the motions you've created, you can save them, and we can put a few exercises together and make a program for patients, for instance, and use these as your training or exercising therapy system. And here's an example of, we're also experimenting with using Kinect. So, and for this kind of upper body application, it works very well because, as you know, Kinect comes, the API comes with a body tracking algorithm inside. So we get for free the position of the joints, the joint angles. We can easily extract that and map to our characters. And actually, here is an example of using this application running 2 times on the left and on the right, 2 instances. Each one has 1 Kinect, and we're sending to each other the motions collected by the sensors. And then we can visualize these motions in different ways, one on top of the other, or side by side in 2 different characters, right? And here what you see is an example of using, on the right side, the Kinect application, the Kinect version of it, and on the left side, the full Powerwall version of it, and the application in the end is the same, but we could imagine of having higher-end systems where we can better visualize some data in some facilities, but the low-cost system being easier for people to use at any location. Now, we are also applying the same concept for hand therapy. And again, the idea is we can have hand exercises specified by therapists, and then we can model them by capturing these exercises. And in that case, it is possible to use data gloves. Maybe we don't need to do that often, and it's easier to track with data gloves. But then we would like to track patients, the hands of the patients, and see how, and have them to follow these exercises. And of course, a camera-based or Kinect solution would be ideal because then there is no devices. It's cheaper and easier to use. But then at that time, we need to develop our own solutions for tracking the hand, and that's what we're doing right now. And with that, again, we can have real-time feedback, logging, and assessment tools together in such systems. And therapy programs can be developed. And depending on the goals, we may need to have a robust tracking to really look into evolution of range of motion for each of the joints, or maybe just a more loose tracking more on the activity of the hand would be enough just to be sure that the patients are moving their hands in some desired way. So we are looking into all these possibilities with physical therapists, and we are working on tracking algorithms for extracting the hand out of the Kinect data, right? And here we are just seeing is just segmenting out the hand out of the full information of Kinect. And so far, Kinect has been mainly built to capture a large volume of space, and we really have to use a subspace of this information to identify the hand, and from there, fit some skeleton there to get joint angle information. Okay, so finally, I hope, as main conclusions here, I hope I could show you that it is possible to design efficient search spaces that would allow some of these motion planning algorithms to run more efficiently and more realistically in order to have these close to real-time, at least at interactive rates, virtual characters are able to address a variety of demonstration tests to different environments and generic targets and environments. And once we integrate that with some user interaction, then we have several interesting applications to explore and allowing these interactions with virtual characters. So far, on the application side, I have just presented following motions, following exercise, but of course, all of these more complex task execution could be added without much modification. We'd like to have the users to repeat tasks, and we could use the same kind of sensors to track how the tasks are being repeated. We can also track, of course, the position of objects that are being manipulated by the user. And we can monitor that and replay with solutions that will model for the virtual character to demonstrate. And I'll just display here some acknowledgements of some of the graduate students involved in this project, collaborators, and the funding agencies like Citrus here. And I'll just stop here. Thank you.
So do we have any questions for
For your physical therapy applications, for example, what kind of computing power do you need? Because is this something you could run on a typical laptop, or do you need larger equipment, and how fast?
So for the kind of applications that I showed in the videos here, which is just playing exercises and tracking people following them, any normal notebook computer would be able to do it, right? It's just one Kinect placed on the USB port of a computer. It cannot be a very lightweight computer, so Kinect demands some computing power, right? But it doesn't need to be a high-end laptop computer. Now, we can imagine having this running very well on game consoles, right? Like Xbox, for instance, has efficient cards inside, and they're using that for games, right?
So do we have any other questions? Oh, right here.
The example you brought with a physical therapist, what's the advantage of going through an avatar versus just taking a videotape of the physical therapist directly?
So that's a very good question. So, well, there are several advantages that we believe can be explored. One of them I already mentioned. It's much easier to stream in terms of the remote collaboration because we just need to send the joint angles, right? The other advantage is that it is easier to model and variations of motions. And usually when we would like to record example exercises with video, it requires some more effort. The video has to look good and so on. And sometimes it is easier just to have the virtual character, and you can change the appearance of the character, right? Now, we have not looked into if the appearance of the character improves or not. Does it bring a benefit in terms of having an easier or more motivation for the patients to follow that motion, right? Is it a benefit or not in terms of having the application more interesting to use between the video or the virtual character, right? But another advantage that we have is that with the video, you just have a flat video playing the exercise, and with the 3D character, you can rotate, see from different points of view. So while the patient is playing the motions, the therapist on the side can be looking from different points of view, top, left, right, and analyzing where and how the patient is performing the exercises. So the advantages to manipulate the 3D model are clear. Now, in terms of acceptance from the user side, that's something still to look into, right?
Okay. Well, I just want to thank you again for giving us a great talk today.
Thank you.